Right. Yes. So the agenda for today, actually, according to the schedule, covering multi-class SVM and um, dimensionality or feature selection techniques by Dr. Sanja ma'am. But today, Sanja ma'am has got some urgent work. So I'll compensate the session with decision trees, and tomorrow, madam will take both the sessions. Um, Feature selection and dimensionality reduction techniques. Okay, so this is a small change in the schedule, and along with multi-class SVM and decision trees, I'll also cover hidden Markov models, which we have missed in the one of the sessions. Due to time limit, I didn't cover that hidden Markov models. So today I'm gonna cover that hidden Markov models. So we're gonna discuss multi-class SVM, hidden Markov models, then decision trees, right? So the three different topics. So, so this you need not require much introduction about what is multi-class classification, right? Is my screen visible? Is my screen visible?
Yes, sir.
Yeah, right. Okay. So you did not need much introduction about what is multi-class as well, isn't it? So in the case of multi-class classification, an input belongs to one of the k classes, where k greater than 2, right? So input associated with the class label, one of the k classes, and the prediction is given a new input, predict the class label from one of these k classes. Okay, so and each input belongs to exactly one class, not more, not less. Okay, so if it belongs to more than one class, it means the problem is different. The problem is not multi-class classification. The problem is multi-label classification. So we're not going to cover multi-label classification here. We're just talking about multi-class classification where each instance belongs to only one class out of the k classes. Right. So this is the problem. Right. So like for example, if you see the applications, application is handwritten character recognition where the input is handwritten character or the output is which character it is. So there may be 26 number of classes if you consider uh, caps and smalls as same. If you consider them differently, there may be 52 classes and input and object detection. In that case, input is a photograph of an object and the output is which object it is from a set of categories. Like for example, if you take Caltech 256 data set, we have objects like car, tire, duck, laptop, something like this, right? So the point is the input is belong to one of the k classes. Okay, there are multiple classes, more than two classes. Similarly, if you take a news article, which section of the newspaper should it belong to? Should it belong to political news or should it belong to cinema news? Or should it belong to crime news? Should it belong to international news or should it belong to national news? Right, you can categorize them into different labels and keep it in an appropriate folder. If you take an email, which folder should an email be placed into? Should it be placed in primary folder or social folder or updates folder or forums folder, right? Or given an audio command given to a car, which set of actions should it be executed? All these are the example applications of the multi-class classification problem. Okay, but if you take the SVM that we have discussed in the previous session, SVM is essentially for two-class classification, so it can only do binary classification, right? So how do you extend this binary SVM to a multi-class classification problem is what we are dealing with in this session. Okay, so there are many approaches to handle multiple classes. One way is combining multiple binary classifiers and come up with a solution to the multi-class classification problem. Another one is training a single classifier by by using the multi-class optimization objective for the constraint classification, right? So we're going to discuss the more details of this in this session, combining multiple binary classifiers. So these are the different approaches that combines multiple binary classifiers and provide a solution to the multi-class classification problem. So all of them trying to combine multiple binary classifiers in some way or the other, such that you can provide a solution to the multi-class classification problem. The most popular of them are one against all, one against one, decision tree structured, binary tree structured as well, error correcting code. So we're going to see all five of them. Um, Let us start with one against all. So what is one against all? As the name is itself describing everything, we're going to learn classifiers with one class as a positive instances and rest of the classes as a negative instances. Right? One against all. So here the assumption is each class individually separable from all other classes. What is the assumption? Each class individually separable from all the other classes, right? So we require k binary SVMs here because we have k classes and each one of the binary classifier is responsible to separate ith class from the rest of the classes. Instances of the ith class from the rest of the classes. So ith classifier is responsible to separate instances of the ith class from the rest of the instances. Right? And the final prediction is given by the classifier with the highest output value. So here the training is, each classifier is trained with the entire training set because every time you are using the whole training data set. And the test sample is tested with k SVMs. And the prediction is winner takes all. So you're taking k classifiers W transpose IB for I equal to 1 to k. Okay, so whichever the class that maximizes this quantity, you're classifying it as that class. Okay, so let us see it visually for better understanding. So given three classes, let's suppose we have three classes, instances from three classes, red, green, and blue. Okay, so one again is all learns three classifiers. One is the blue classifier with separate blue points from the rest of the points. The other one is the red classifier with separate red points from the rest of the points. Another one is green classifier with separate green points from the rest of the points. Okay, so W transpose X plus B greater than 0 for all the blue points. W red transpose X plus B greater than 0 for all red points. W green transpose X plus B greater than 0 for all the green points. And the prediction is based on winner takes all. It means given a new instance, you give it to all these classifiers. You give it to W blue, you give it to W red, you give it to W green. Okay, so whichever is giving the maximum value, you classify it as that. Okay, very simple strategy, right? Very simple strategy. You are learning three. If you have three classes, you are learning three classifiers. Suppose if I have 10 classes, then how many classifiers do I require to learn? 10 classifiers I need to learn, right? And when you are classifying a new instance, I need to give this point to all the 10 classifiers. So I need to check this against all the 10 classifiers at the time of testing. Okay, just remember that. So what are the problems? Problems with this. One against all may not always work. Like for example, if you see this set of points, black points as you can see in the figure, black points are not separable with a single binary classifier. Like for example, if you see the blue classifier is ignoring them, red classifier is ignoring them, and green classifier is also ignoring them. So the blue points are the points that are not covered by any of these classifiers. Okay, so the decomposition will not work for these kind of cases. So if you summarize the one against all classification, it is easy to learn. We use any binary classifier learning algorithm. You need not restrict to SVMs. Problems with this are no theoretical justification for this. Why is it working? And there are calibration issues. What are the calibration issues? We are learning this classifier separately. The learning for this is separate from learning for this and learning for this. Okay, so when you're learning them separately, there is no reason that the score should be in the same numerical range. The score can be in a different range because the initialization is different and the learning phase is different. You're not learning them simultaneously, you're learning them individually and independently. So there is no reason for them to be in the same numerical range. Okay, so they may be in different ranges. So you cannot compare the scores produced by K classifiers that are trained independently. Right? So this might not work always. Okay? It works fairly in many of the cases practically. Though there is no theoretical justification for this, it works fairly well in many of the cases practically when you implement this practically. So that is the summary of one against all classification. Next one is one against one classification. We also call this as all against all classification. Okay, so in the earlier case, if we have three classes, 1, 2, 3, what are we doing? Is the audio not clear?
It is clear, sir.
Okay, so, Srinivas, please check your audio connection. Okay. All right. Okay. So if you see the one against all classification, suppose if I have three classes, what am I doing? I'm learning 1 versus 2, 3, and 2 versus 1, 3, 3 versus 1, 2. Right? Whereas in case of one against one, I learn the classifier between every possible classes, pair of classes, every pair of classes. Every pair of classes possible. Suppose if I have three classes, 1, 2, 3, how many pairs of classes possible? 1, 2, 1, 3, and 2, 3. Right? So I'll learn a classifier 1 against 2. I'll learn a classifier 1 against 3. I'll learn a classifier 2 against 3. Right? And if I have 4 classes, then I'll also learn 1 against 4. I'll also learn 2 against 4, 3 against 4. All these I will learn. Right? So every pair of classes. So the assumption here is every pair of classes is separable. And the learning here is for every pair of labels, we create a binary classifier with positive examples as all examples with label J and negative examples as all examples with label K. So we try in a classifier between every pair of classes J and K such that all the instances from J class is labeled as positive and all the instances from K class are labeled as negative. So if I do it, how many classifiers do I need to learn? If I have K classes, if I have K classes, how many pairs are possible? How many combinations are possible? KC2 number of combinations are possible. KC2 number of pairs are possible, isn't it? So what is KC2? K into K minus 1 by 2. Binary SVMs we need to learn. And each classifier gives one word to its preferred class. And the class with most number of words is the winner. Right? For example, if I learn this, excuse me. Suppose if I learn 1 versus 3, 1 versus 2, 1 versus 3, 2 versus 3. Okay, given a new instance, I give it to this classifier. Let's say it is classifying it as 1. So class 1 has got one word. Initially all words are 0. Okay, so this classifier classifying this as 1. So class 1 has got one word. Give it to this classifier. Suppose this is also classifying it as 1. Then you increment the count for 1. Class 1 has got 2 words so far. And give it to this. Let's say this is classifying it as 2. 2 has got one word. So on the whole, class 1 has got 2 votes, class 2 has got 1 vote, class 3 has got 0 votes. So which label would be assigned? The class with most number of words, that is class 1. Right, good. So that is how we assign a label in 1 against 1 classification. So every pair of label, the assumption is every pair of label is linearly separable here. And when a pair of label is considered, all the other are ignored. It means you are not considering the whole training set at the time of training. For training one classifier, you're only considering the subset of the training set. So because you're only considering the subset of the training set, and this subset of the training set may be small and may lead to overfitting problem. And the prediction might be unstable sometimes. Like for example, what if the two classes get the same number of words? Then you have to use some tie-breaking rules. And another problem here is that you have to learn order of k-square weight vectors to train and store. Then k into k minus 1 by 3 is order of k square, right? You have to learn order of k square, and at the time of testing also, you need to test it against order of k square classifiers. So each test instance is tested against k into k minus 1 by 2 number of classifiers. Okay, so that is the problem with this. Both training complexity is high and space complexity is also high. Right. So to reduce that, to reduce the testing complexity, time complexity at the time of testing, these classifiers are organized in a tree-like structure, graph-like structure. Okay, in a certain manner such that you can reduce the number of testings at the time of testing. Okay, so that is DAG SVM, Directed Acyclic Graph Structured SVM. So here the training is same as OAO. Here also we learn a classifier between every pair of classes. We learn a classifier between every pair of classes. But the way we test here is not same as in case of 1 against 1. What are we doing then? We are giving it to each and every classifier. And each and every classifier is giving us one vote against one class. And finally, the class with most number of words will be the winner. But here we're not doing that. We are organizing these classifiers in a certain manner such that the number of comparisons would be reduced. Number of testings would be reduced. Okay, so as you can see here, I have 5 classes here, and these are all the pairs of classes. 1 versus 5, 1 versus 4, 2 versus 5. All these are the pairs possible, and learning a classifier between every pair of classes. Okay, so and 1 versus 5 is organized at the root node, which means the very first class and very last class. Right? So this is at the root node. Here I am checking whether it is 1 or 5. Suppose if the classifier is saying that it is 1, if the classifier is saying that it is 1, then what is that means? It is also classifying it as not 5. Agree? If the classifier is saying it is 1, it means it is also classifying it as not 5. Agree with me?
Yes, sir.
So it is not 5. So therefore, any combination with 5 you can ignore. So you cannot check any combination with 5. So you can ignore all of them. Right? So you're coming here and here checking 1 against 4. Suppose if the classifier is saying it is 4, it means it is also saying that it is not 1. So therefore, you can omit all the combination with 1 in the succeeding levels. So all this can be ignored. So now you're coming here and checking 2 versus 4. Suppose if it is classifying it as 2, it means what? It is saying it is not 4. So therefore, you can omit all the combinations with 4 in the succeeding levels. So this also can be ignored. Finally, you're coming here and checking 2 versus 3, and it will classify it as either 2 or 3. Okay, so if you observe here, how many classifiers are you checking to classify a new instance if you have 5 classes?
4.
We are checking 4 classifiers. So in the case of 1 against 1, we were checking k into k minus 1 by 2 number of classifiers at the time of testing. Here it is just k minus 1. So it is reduced from order of k square to order of k. Right? So that's the advantage of DAG SVM as compared to OMO. Okay, it reduces the test time. So can we reduce it further, both in terms of the training complexity and the testing complexity, right? So from there, the concept of tree structured SVM came into picture. So the binary tree structured SVM organizes the classifier in a binary tree like fashion. So here, instead of checking for 1 against 1 with each and every node, we have this subset of classes as one class and the remaining classes as the another class. Like for example, if you see here, 1, 2 is positive labels and 3, 4, 5 is the negative labels. Let's suppose it can be other way also. Right. So, and once we say that it is 1, 2, we can ignore 3, 4, 5. So, you can ignore this branch. So, this can be completely ignored. So, you're coming here and checking 1 versus 2. So, it will classify it as 1, either 1 or 2. Okay. So, it organizes the classifiers in a binary tree structured manner. And at every node, we are checking checking one condition, that is to which subset of the classes this instance belongs to at each and every node. Finally, if you follow the path, it will be classified as one of the classes. Okay, so if you have k classes, k minus 1 SVMs are required. So if you see how many classifiers here, this is one classifier, this is another, 3, 4. 4 classifiers are required with the 5 classes. So if you have k classes, then k minus 1 classifiers are required. And how many classifiers you need to check if it is a balanced tree? If it is a balanced tree, then how many classifiers you need to check? Height of the tree, right? And height is log k base 2, isn't it? So I'll show you another example. Let's suppose you have 8 classes. 1, 2, 3, 4, 5, 6, 7, 8. Let's suppose at the root node you are checking a condition of 1, 2, 3, 4 versus 5, 6, 7. When you come here, let's suppose you are checking 1, 2 versus 3, 4, and you are checking 5, 6 versus 7, 8 here. And here, let's suppose 1 versus 2 you are checking and 3 versus 4 you are checking. Here 5 versus 6, 7 versus 8. It need not be this way, but ideal condition I am telling you, very balanced tree. Right? So what is the height of the tree here? 1, 2 and 3. Isn't it log 8 base 3? Sorry, log 8 base 2. Isn't it? Isn't it equal to 3?
Yes. Yes, sir.
Right. So the height of the tree, if it is balanced, it is log k base 2. So how many number of classifiers you need to check at the time of testing? You need to check only log k base 2 number of classifiers to classify a new instance. Right. So you are reducing the testing complexity from order of k to order of log k. Drastic improvement. And at the time of training also, you are training only k classifiers. Order of k classifiers, sorry, k minus 1 classifiers, which is order of k. We're not trying order of k square classifiers. Okay, so which is a dramatic improvement in terms of training and testing complexity. And performance of all the models is more or less same at this stage. Only thing that is different is training and testing complexities. Accuracy wise, more or less they give the same accuracy. Right? And so in the binary tree structured SVM, hierarchical multi-class model binary structure is the best option, looks like. But the critical decision is binarization, isn't it? Because if everything is giving the same accuracy, but if the binarity structured SVM is improving in terms of time and space, then it looks to be the best option. But the critical decision is binarization. Which set of classes should go to the left side? Which set of classes should go to the right side? Right? Which set of classes should be the positive class and which set of classes should be the negative class? So that decision is binarization. Right? And so how do you do binarization? So binarization is recursively dividing the classes into two disjoint groups at each and every node. Okay, so we can divide these K classes into two groups in many ways. These are some of the popular grouping techniques. Divide based on the class labels, divide based on the feature vectors, or hybrid method where it uses both class labels and feature vectors. Okay, so the idea is the intra-cluster distance should be minimized and inter-cluster distance should be maximized when you're grouping them. Right? It means that distance from points in two different groups should be maximized. Distance within a one group must be minimized. Okay, so that's the idea. So you will be doing, you're dividing all the classes into two groups, learning a classifier, going to the next level, and again dividing all the classes at that level into two groups, again learning the classifiers and so forth. Okay. So have you understood this? Any query in this?
Sir, excuse me, sir.
Yes, Prashant.
Sir, so why is there no chance of calibration problem in this issue, unlike the one versus all? Because here also we are learning different classifiers, which are not related. So why it is
You
not
mean the
considered?
class imbalance problem you were talking about?
Yes, sir. I mean, yeah. Sorry for delay. I mean,
Yeah.
when addressing the problem of one versus all, uh, why
Yeah.
didn't we consider a calibration problem?
Yes, the
For
problem is there. Yeah, problem is there that class imbalance problem will definitely come. It will be biased to the class with more number of instances always. Yeah, that is another problem with one against one. Thanks for reminding. You mean to say the calibration issues are like the one that I mentioned in the one against all?
yes, sir.
Like,
Yes,
but
yes.
there, if you see, yeah, let me think about it. Give me a second. No, here may not be because your decision, your prediction is not based on the winner against all. No? These are independently tried and independently tested also. But if you say that they're independently tried, but they're not independently tested, you're testing them with the same, I mean, at the same formula, isn't it? So
Yes.
if you see one against all, so what are you saying? Argmax of W transpose XI plus B. Okay, so they're trained independently, but you're comparing them at one place, right? But here you're not comparing them at one place, right? You're comparing them at different levels. So it is tried independently and also tested independently. Okay, and taking a decision whether it is 1 2 versus 3 4 5, 1 2 or 3 4 5. So once it is done, it is thrown away. Then you're coming to the next level and asking 1 versus 2. So this is tried independently and also tested independently. You're not depending on this.
Yes.
Depending, yeah, not depending in the sense you're not depending on that classifier for this classification. Okay.
Yes. Okay,
So
sir.
once it is decided, so no calibration issues. I mean, the way you are intentionally. But one problem is there in the one against all. Another problem, the class imbalance problem. Like because one against all means only one class is in positive side, rest of them are negative side. So there is a class imbalance problem. Very few instances belong to one class, more instances belong to the other class. So in that case, classifier may bias towards one particular class, one particular set.
Yes. So one more doubt, sir. Here we are doing a class grouping of our class levels. Then we are using for testing, and it's a kind of two-level multi-level classification kind of thing. A kind of
Yeah, two level.
yeah.
Yeah, it is two level. That is actually disadvantage of this weakness. It is a suboptimal two-stage procedure. You can see this. The
Okay,
tree
sir.
construction is different from the classifier learning.
Yes,
First,
sir.
we use some measures about the separability to group them. Then we find the decision boundary to separate them. Okay, so here the measure of separability different from the separation of margins.
Yes.
Okay, so that's actually weakness of this. Strengths are
Okay.
training and testing complexities. Both of them are reduced. Early termination and discriminating order is there. Stage-wise linear separability is there. So these
Yes.
two we'll see with examples. What is discriminating order and stage-wise linear separability? And weakness is class centers or mean distance is used. So a class is taken as a single unit by default in most of the cases. Alright, so
Yes.
we'll see what is discriminating order. Yeah, Prashant, do you have any query?
No, sir. Thank you, sir. Yeah, I
Yeah,
got
yeah,
it.
yeah, yeah. So discriminating order and stage-wise linear separability, we'll see this. So if you see this toy example one, so this is one class, this is second class, 3, 4, let's see. So if you apply one against all, is this linearly separable? So can you learn and classify like this or like this without misclassifying anything? No, right? It's not possible, isn't it? Right? But if you see, there is a stage-wise linear separability in the data set. Suppose if you choose to classify this 1, 2 versus 3, 4 first, then there is a linear separation. Next, if you choose to classify 1 versus 2 here and 3 versus 4 here, linear separation there also. So the discriminating order is important here. So the discriminating order is learned in case of this binary T-structured SVM, but not in the other cases. Okay, so one against all tag or one against on all that. Right. So another example, this is also the same 1, 2, 3, 4. So this, if you learn this classifier first, then these two next, then there is a stage-wise linear separability. So the discriminating order is also important to classify the data, and the discriminating order is preserved in the case of this binary T-structured SVM. This is another advantage of this binary T-structured SVM, along with improving the complexity, training and testing complexities. Right. So the next one is error correcting output codes. So if you see for binary tree structured SVM, we need to learn order of k classifiers. K1 is one classifier which is order of k. At the testing time, we are reducing it to order of log k base 2 to test. Okay, but at the time of training, we're still learning k classifiers, k minus 1 classifiers. Can we reduce it? Yes, we can reduce it using error correcting output codes SVM. So each binary classifier provides one bit of information here. And with k labels, we only need log k base 2 bits. Okay, so this may be a bit confusing. You may not be getting what am I talking. So I'll ask you a very general question. So how many bits do you require to represent 8 numbers, 0 to 7? Suppose if I ask you to represent 0 to 7, how many bits do you require? 3 bits, right? So 0 can be represented as 000, 1 can be represented as 001, so on. 7 can be represented as 111. Okay, suppose if I ask you to encode 8 classes, 8 classes can be anything. Let's say 0 to 7. Or it can be some ordinary class also, any classes. Suppose if I ask you to encode using a binary string, 8 classes, how many bits do you require? You require 3, right? Why 4, madam? 3, right? Yeah. So 3 bits you require. So you can represent class 1 as 000, class 2 as 001, class 3 as 0010, and so on. Class 8 as 111. Okay. So now suppose if I represent this. Okay. So if I represent it as a binary string, how can you see each column? Isn't it a binary classification? How can you see each column? Isn't it a binary classification? It's a binary classification, right? Where you have only zeros and ones, right? So you learn a classifier 1 here, classifier 1, learn a classifier 2 here, and learn a classifier 3 here. Okay, so what am I saying? If the data is given to you, where should I write? Okay, let me find some space. Okay, let me erase this. Okay, if the data is given to you, example 1, example 2, so on, example n. Okay, so each of them is represented with feature 1, feature 2, so on, feature d, and target value. Target value y. So this is x1 to xd and this is y. Right? This is object 1 or instance 1, example 1, whatever you call it is. So this is a feature vector and the corresponding label. Let's say it is 1. This is a feature vector corresponding label. Let's say it is 2. Another, let's say it is 3. Another, let's say it is 2. Let's say it is 1. Let's say it is 2, something like that. Okay, suppose if you have 8 classes, something like this, then you represent this one as 0, 0, 1. You represent this 2 as 0, 1, 0, and so on, 0, 1, 0. Okay, now you have got the examples and take this label first time. Example, this is x and this is y. Learn a classifier 1, CLF 1. Now this time, second time, you take this with this second column. You get CLF 2. Third time, you take this with the last one. Right? So you will get CLF 3. So when the new instance comes in, you give it to all these 3 classifiers. CLF 1, let's say it is predicting it as 0. CLF 2, let's say it is predicting as 1. CLF 3, let's say if it is predicting it as 0. Okay, so this is the bit string that you have got. Now you decode it. If you decode, what would you get? 2 would get, right? So you classify it as 2, class 2. Okay, so how many classifiers you are training here? If you have k classes, you're just training log k base 2 number of classifiers. So there is a drastic improvement in the training phase. And the test time also you are checking only log k base 2 number of classifiers. Okay, so everything is looking very fine. But what is the problem with this? Problem with this is, even if one of the classifier makes a mistake, then the whole prediction will be wrong. Isn't it? Even if one of the classifiers makes a mistake, the whole prediction will be wrong. Okay, so how do you solve that? To solve the problem, what are we doing is, we are adding additional bits randomly. In addition to this representative bits, we are adding additional bits. And this number of additional bits that we take is constant number. Okay, we fix that some constant number of bits we add and we generate those bits randomly. Okay, and we assume that this is the encoding for class 0, this is the encoding for class 1, and so on. And we learn the classifiers for all these log k base 2 plus some constant number of columns. Okay, so these many number of classifiers we will learn. And when the new instance comes, we give it to all the classifiers and we get the bit string. Okay, so once we get the bit string for the new instance, we look for the decoding which is close to this. Okay, suppose if the binary classifiers together predicting it as 11010, 11010. Okay, so we'll see which bit string is more close to 11010 using Hamming distance. So which bit string is more close to 11010? 6 is more close to 11010. There is only 1 bit difference between them. Whereas if you take other bit strings, 2 or more bits different. Okay, so 11000 is more close to 11010. So 11010 is our prediction, and among the encodings, 11000 is more close to this. So if you encode this 11000, sorry, decode this 11000, what are you getting? You're getting 6. So we'll classify it as 6. Right? So, but still, this complexity is order of log k base 2 because you're just adding constant number of classifiers. So the complexity is still order of log k base 2. Okay. So that is how you can avoid this by using the redundant bits. Okay. So any queries so far? That's all we have done. So we'll go to hidden Markov models quickly if you have no queries. Any query? Yeah, Prashant.
Uh, Sir, can we have any source where it proves that, I mean, it is mathematically valid that if you learn the binary encoding classifiers, log k classifiers, it is equivalent to learning the original classifier. When can we have, I mean, how is that mathematically valid? I mean, it seems intuitive, but somewhere can we? Is there any source or any where we can get the idea? Because here it may be out of scope to discuss that, but
No. Let me try to understand your problem, question. Okay.
yeah,
So you are
yeah,
asking that is there any theoretical justification that it works?
yes, or proof of correctness, or any.
No, there is no theoretical justification for this. Like similar to the case of that one again install, there is no theoretical justification. But yeah, it is the intuitive idea. Based on that, practically it works well.
Okay, sir,
Yeah,
fine. Sir. But it's very interesting. So thank you.
yeah. All right. So any other query? Okay. Shallow. Without wasting time, let's proceed to hidden Markov models because this is extra topic that we have to cover today. Hidden Markov models. This we supposed to discuss on the third day, I think. Probability and statistics when we were discussing Bayesian learning. Because the Bayesian learning itself took 1.5 hours, so we couldn't cover this hidden Markov models there. So let us try to cover this hidden Markov models here, right, quickly in 45 minutes time. Right. So this is the outline. We're going to discuss Markov models and Markov assumptions, and then we're going to discuss hidden Markov models and some of the examples and application of this hidden Markov models in speech recognition. Right. So this is what we're going to cover in this particular topic. So let's talk about the weather. Weather. All of you know the weather. Weather can be of number of types, but we are assuming to be 3 types: sunny, rainy, and cloudy. And also assume that weather lasts for the whole day. So it cannot be that half of the day is sunny and half of the day is rainy. Though it is possible in real time, we are just assuming just for the simplicity weather lasts for the whole day. Okay, sunny, rainy, and cloudy. So what is weather prediction? Weather prediction is like given the weather information for n days, you need to predict what is the weather for the n+1th day. So that is the weather prediction, right? So it is all about trying to guess what the weather will be like tomorrow based on the history of observations of weather. Right. So to do that, what we do, we collect statistics on what the weather was like today, what the weather was like yesterday, day before, and so forth. So what are we doing? We're trying to guess what is the weather on nth day given observations about n-1 days. So this Q1 is the state on the nth day, whether it is rainy or cloudy or sunny. So this information is given for n-1 days. You need to predict what is the probability that nth day is rainy, or what is the probability that nth day is cloudy, or what is the probability that nth day is sunny. For instance, what is the probability that day 4 is rainy, given that day 3 is cloudy, day 2 is sunny, and day 1 is sunny? Right. So this is what we are interested to predict. Given the information about n minus 1 days, you need to predict what is the weather for nth day. Or given the information about n days, what is the weather for n plus 1 day? Okay. So this sequence is important here. So we need to estimate probability of Qn given Qn minus 1, Qn minus 2, so on, Q1. Looks fine, but what is the problem? What is the problem? How many probabilities you need to store if you have to estimate this? What are the possible sequences if you have n days and three different, for each of the state can take three different values, isn't it? So each of them can take three different values and there are n such things. Let's say n is equal to 6. Okay, so how many probabilities that you need to store? You need to store, for this, you need to store 3 power 5 statistics. Right? So the different possibilities are there. The sequence could be like sunny, 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 all sunnies, all 5 days sunnies. This could be like sunny, 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 raining, or sunny, 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 cloudy. All these sequences are possible, right? If you consider all the possible sequences, that is 3 power 5, which is a huge number, 243. Past histories you need to store. What if n is 100? 3 power 100. What if the number of states is not 3, some 10? 10 power 100. Can you imagine that number? Is it possible to store that number? Those many number of statistics? Not at all, right? So therefore, we have to make some assumptions about this. Okay, so that assumption is Markov assumption. So to simplify this, we are making some assumption. Assumption is that nth state is only depending on n minus 1 state. So given n minus 1 state, nth state is independent of all the other states. That's what the assumption. Okay, so more formally, we say that probability of Qn given Qn minus 1 to Q1 is equivalent to probability of Qn given Qn minus 1. Means what? We are assuming that nth state is not depending on Qn minus 1 to Q1 given Qn minus 1. Following me? Is this okay? Or lost in these notions? No, right? Yeah, right. So given n minus 1 state, you are assuming that nth state is independent of all the other states. So this we call it as first order Markov assumption. First order Markov assumption. So if you suppose, if you assume that nth state is only depending on previous two states, not just one state, previous two states, it means Qn minus 1 and Qn minus 2. Then it is second order Markov assumption. Okay, suppose if you assume that nth state is depending on previous k states, not just one or two, previous k states, then we call it as kth order Markov assumption. But usually when somebody says Markov assumption, they refer to first order Markov assumption. If they don't specify any order and just saying Markov assumption, it means it is first order Markov assumption. So using this assumption, what is the joint probability? Without this assumption, what is the joint probability? Joint probability of Q1 to Qn. What is the joint probability? This is equivalent to probability of Q1 times probability of Q2 given Q1 times probability of Q3 given Q2 and Q1 times probability of Q4 given Q3, Q2, Q1 and so on. Okay, so because now we're assuming that nth state is only depending on n minus 1 state, so you can ignore this, you can ignore these two and write it as probability of Q1 times probability of Q2 given Q1 times probability of Q3 given Q2 times probability of Q4 given Q3 and so on. So which is equivalent to product of probability of Qi given Qi minus 1. The same thing is written this way. Right. So the joint probability of Q1 to Qn is product over probability of Qi given Qi minus 1 for I equal to 1 to n. Right. Simple. Right. So now if you see we only need 3 square, that is 9 number of probabilities. We don't require 243, 3 power 5. We just need 3 square, which is 9 numbers to characterize the probability of all the sequences with this assumption. Okay, so what is the probability of today's weather is sunny given the what is the probability that tomorrow's weather is sunny given today's weather is sunny, which is 0.8. Okay, so the transition from sunny to rainy is 0.05. The transition from sunny to cloudy is 0.15 and so on. Okay, so remember this assumption may be or may not be a valid assumption depending on the situation. But we use this assumption to simplify the situation. Whether it is valid or not valid, we use this to simplify the situation. It may be a valid, may not be a valid. It depends on the situation at hand or the application at hand. Right? Most of the time it may not be valid. Right? But we use this to simplify the situation. Right. So let us. So this can also be represented using this state diagram like this. So we can use the probabilities to draw a probabilistic finite state automation, like in which the states are the different weathers. Sunny, foggy is equivalent to cloudy in our this thing, and rainy. And these are the transition probabilities. Transition from sunny to foggy is 0.15. You can see that. Where is that? Say 0.15. Sunny to cloudy. Sunny to rainy. Sunny to rainy is 0.05. Sunny to sunny is 0.8. 0.05. Sunny to rainy and sunny to sunny is 0.8. So just capture this using your mobiles because there are some questions based on this. So please take a photograph of this. So there are some problems so that you can solve that and solve them and answer. So take a photograph of this or this, both are fine. Both are same. So have you taken? Shall I proceed?
1 minute, sir.
Yeah.
Sir, please show the previous slide, please.
Yeah. This one only, right?
Yes, thank you, sir. Yes, sir. Thank you, sir.
So shall I proceed now? Okay, I'm proceeding. Okay. So the questions. Given that today is sunny, what is the probability that tomorrow is sunny and the day after is rainy? So this is what we are interested in. What is the probability that Q3 is rainy and Q2 is sunny given that Q1 is equivalent to sunny? So how do you write it? You can write it as probability that Q3 equal to rainy given Q2 sunny, Q1 sunny times probability of Q2 sunny and Q1 sunny. So already someone computed. Very good. 0.16 somebody said. Let's see whether it is correct or not. Right. So using the Markov assumption, how can I write this? Probability of Q3 is raining given Q2 is sunny. I can ignore this, right? Because we are assuming that Q3 is only depending on Q2, not Q1. Given Q2, Q3 is independent of Q1. So I can write this as probability of Q3 rainy given Q2 sunny times probability of Q2 sunny given Q1 sunny. So substitute, what is the Q3 rainy and Q2 sunny? I mean, what is the transition probability from sunny to rainy? Sunny to rainy. I don't have the table. You only have. Sunny to
0.05,
0.05 and sunny to sunny
0.8,
0.8. So multiply them 0.00, 0.05. Yeah. So 00, sorry, 0.04 is the answer. Right. Next question. Given that today is cloudy, what is the probability that it will be rainy 2 days from now? So tomorrow information is not given to you. What is given to you? Today is cloudy. We are asking about probability that what is the probability that it will be raining 2 days from now? Day after tomorrow. What is the probability that day after tomorrow is raining? Okay. So what are the possibilities for tomorrow? Tomorrow can be anything, right? Tomorrow can be sunny, tomorrow can be rainy, tomorrow can be cloudy, isn't it? So the possible ways to reach from cloudy today to rainy 2 days from now is cloudy, cloudy, rainy, or cloudy, rainy, rainy, or cloudy, sunny, rainy. So we know this and this. We don't know this. So make assumption for all the possibilities: cloudy, rainy, sunny. Okay, so all three possibilities, let's compute the probability for all three possibilities and take sum over that. Right? So therefore, we have to sum over all these parts. So probability of Q3 is rainy, given Q1 is cloudy is probability of Q3 rainy, Q2 cloudy, given Q1 cloudy, plus probability of Q3 rain, Q2 rain, Q1 cloud, and probability of Q3 rain, Q2 sunny, Q1 cloudy. So all three possibilities to Q2. So can you compute this? So isn't it equal to this? Probability of Q3 given rainy times given Q2 cloudy times probability of Q2 cloud, Q1 cloud. Okay, and similar way you can compute the other two also, and you would get 0.34. So I'll give some time to look at this and observe this. So go through it and observe. If you have any query, you can raise. You're always welcome. Fine? Is that looks fine? Understood?
Yes, sir.
Okay. So not many S's. Okay. Okay. All right. So, chalo, let's proceed. So now the question is, these are all the Markov models. What is hidden Markov model, and what makes the model hidden? So what makes a hidden Markov model? Right. So let us see that. So we have seen Markov models and how to estimate the probabilities using Markov models and Markov assumptions. Now the question is, what makes the Markov model hidden? Means what makes a hidden Markov model? Well, suppose you're locked in a room for several days. You're locked in a room for several days and you are asked about the weather outside. You're locked in a room for several days and you are asked about the weather outside. The only piece of evidence that you have is whether the person who is coming to you, who is bringing food for you, whether he is carrying an umbrella or not. This is the only piece of evidence that you have. So the actual weather is hidden from you, but there is some observation with you. What is that observation? Whether the person who is coming to you is carrying an umbrella or not. So we are introducing another one. Actual weather is hidden from you, but there are some observations with you. Based on that observations, we need to tell what is the weather outside. right? Because the actual weather is hidden from you. You need to predict that it is YZ, it is hidden Markov model. So let's assume the following probabilities. Probability of umbrella on a sunny day is 0.1. Probability that your caretaker brings an umbrella on rainy day is 0.8. And probability that your caretaker bringing umbrella on a cloudy day is 0.3. So these are the probabilities, prior probabilities. Okay. And now we have to factor in the fact that the actual weather is hidden from you. And finding the probability of certain weather on an ith day, which means what is the weather on the ith day, whether it is a sunny or rainy or cloudy, can only be based on your observations about this xi. What is xi? Xi is your whether the caretaker bringing an umbrella or not. So that is represented using xi. If xi is true, it means the caretaker brought an umbrella. If xi is false, it means the caretaker did not bring umbrella. Right. So you need to find the probability of Qi, which means the weather on the ith day, based on your observation about ith day, about this umbrella on ith day, which is represented as Xi. So can I use Bayesian theorem and write this as this? I can write that, right? Using Bayesian theorem, probability of Qi given Xi is equivalent to probability of Xi given Qi times probability of Qi divided by probability of Xi. So this is for one day weather. Suppose if you want to find the probability of sequence of days, weather of sequence of days, based on your sequence of observations, then suppose you have a weather sequence Q1 to Qn and umbrella sequence X1 to Xn. Then in that case, probability of Q1 to Qn given X1 to Xn is probability of X1 to Xn given Q1 to Qn times probability of Q1 to Qn divided by probability of X1 to Xn. Same formula. Okay. So here, if you see, we are making some assumptions. What are the assumptions? Assumptions are nth day weather is only depending on n minus 1th day weather, not anything else. So using that assumption, this can be written as this. Product over I equal to 1 to n probability of Qi given Qi minus 1. This we have already seen here. Where is that? Oh, I missed it. Here. So this we have already written. Correct. Right. So another assumption that we are making is our observation is only depending on that day weather. Observation xi is only depending on that day's weather. It means xi is only depending on qi, not anything else. Okay. So using that, you are writing this as this. And we are also assuming that all the individual observations are independent of one another. So using this, you can write this as product over the individual probabilities. Okay, so using the independent assumptions, we are just rewriting these rules, rewriting the probabilities, simplifying the probabilities. Okay. Right. So this is simplified. So we want to draw conclusions about the weather outside from our observations on umbrella. So therefore, you can omit the probability of seeing umbrella because you know that. Because you're observing it now, isn't it? So the probability is 1, probability of seeing that is 1. So we can get measure which is proportional to the probability, which is likelihood. So we are ignoring this denominator term here because we want to draw conclusions based on our observations about that. So you can ignore that and only consider the denominator which is proportional to this. Sorry. Where is that? So probability is proportional to the likelihood and just ignoring the denominator, and the numerator part is this. Okay, so now question. Suppose the day you were locked in, it was sunny. The day you were locked in, it was sunny. The next day, the caretaker carried an umbrella. What would be the weather on the second day? The day you were locked in, it was sunny. Next day, caretaker carried an umbrella. And what would be the weather on the second day? So we calculate the likelihood for the second day to be sunny, rainy, and cloudy. Because we were asking about the second day weather, right? What are the possibilities? Possibilities are sunny, rainy, and cloudy. So what is the likelihood that it is sunny? What is the likelihood that it is rainy? What is the likelihood that it is cloudy? All the three possibilities we will consider, and we will select the one with the high likelihood. Okay. So likelihood that second day is sunny, given Q1 is sunny, because we were when the day we were logged in, it is sunny. So we know that it is sunny. Q1 is sunny. And we also know that X2 is true because the second day caretaker carried an umbrella. Right. So which is equivalent to, according to the formula that just now we've seen, probability of X2 given Q2 times probability of Q2 given Q1. If you want, I can show you that again. Yeah, sorry. This one. Product over probability of xi qi, product over qi minus 1. Okay, so xi qi and q2 qi minus 1. Okay, so qi minus 1, which is q2 q1. Right, this is equivalent to 0.08. Similarly, can you compute the likelihood of cloudy and likelihood of rainy? Try one. Find out the likelihood of raining. Given Q1 equal to sunny and X2 equal to true. What is the likelihood of raining? So what is the likelihood of cloudy? Rainy, they asked rainy, right? 0.1 somebody said.
It's multiplying actually.
Okay, so let me check. So Q2 rainy is 0.04, Q2 cloudy is 0.045. Okay, so you can cross check those who have tried and got a different answer. Yeah, you can cross check. Alright, so we have found the likelihood of all the three possibilities. So what is the prediction based on this? What should be the prediction? Sunny, rainy, or cloudy?
Sunny.
It should be sunny, right? Because it has got high likelihood, isn't it? So the likelihood is 0.08. It is bigger than likelihood of rainy and cloudy, right? Higher than that, higher than them. So you classify this as sunny. Okay, weather on the second day. So it is most likely that the second day weather is sunny. Second example. Suppose you do not know how the weather was when you logged in. So the first day weather you don't know. Caretaker always comes without umbrella for 3 days. Day 1 weather you don't know. And 3 days caretaker brought an umbrella. Calculate the likelihood for the weather sequence. this Q1 to be sunny, Q2 to be cloudy, and Q3 to be sun. So this is sequence, weather sequence. We are talking about the sequence prediction, probability of the sequence, not just one state. Probability of sequence of states. Okay, based on our observations. Right. So, since we do not know the first day's weather, let's assume that all the weathers are equiprobable. So, probability of Q1 equal to sunny is 1 by 3. So, this is the day 1, right? Q1 is day 1. So, let's assume the probability of Q1 is sunny is 1 by 3. And likelihood of Q1 sunny, Q2 cloudy, Q3 sunny, given that X1, X2, X3, all of them are false. Because for 3 days, caretaker came without umbrella. So all are false, X1 to X3. And this is the weather sequence that we are interested to predict. Okay, so using this, you can say probability of X1 given Q2, X1 given Q1, X2 given Q2, X3 given Q3. All the 3 probabilities. We know them. Right? And we also know probability of Q1, which we have assumed to be 1 by 3. Then sequence, probability of Q2 given Q1, Q3 given Q2. Multiply all of them. So you would get 0.0057. Right? So this is how you can estimate the likelihood of a state sequence. Likelihood of a state sequence given observation sequence. Likelihood of a state sequence given observation sequence. So a Trellis diagram can be used to visualize the likelihood calculations of hidden Markov model. Okay, so this is an example Trellis diagram. Are you following me? No problem, right? Are you following me? Any issue? Okay, yeah, cool. Thanks. Right. So if you see this, likelihood calculations can be visualized using this Trellis diagram. So if you see, we have got variables here, A, B. Okay, so this is A, we call it as a transition probabilities. Transition probabilities. Transforming from one state to the another state. Okay, so this is the probability of transformation from sunny to cloudy. This is the probability of transmission from cloudy to sunny. Okay, and this we call them as emission probabilities. Emission probabilities. What is the probability of xi given qi? What is the probability of no umbrella given it is sunny? Or what is the probability that no umbrella given cloudy? Okay. And we also have the prior probabilities, which is what is the probability that sunny is the starting state? What is the probability that rainy is the starting state? Or what is the probability that cloudy is the starting state? This we call them as the prior probabilities. So we have 3 kinds of probabilities. Okay, so hidden Markov model is specified by set of states and the parameters phi, A and B. So just now I have told you A is the transition probability, B is the emission probability, phi is the prior probability. Okay, so the prior probability is probability of Si being the first state of the sequence. Transition probability is going from state Si to state Sj. Going from sunny to cloudy or cloudy to rainy or rainy to sunny, sunny to rainy, all that possibilities. And what is emission probability? Probability of a particular observation given a state. Probability of xt given qt. So hidden Markov model can be specified with a set of states and these parameters phi a and b. Even when you are implementing, you need to specify this phi a b. HMM is the model from sklearn. So import from sklearn, import HMM and try to pass this parameters that is required and try to solve it. Okay, so let us proceed. So these are some useful formulas. Probability, this we have already seen. All this, just to summarize in a more formal way, I'm just giving you these formulas. Probability of state sequence. What is the probability that Q1 sunny, Q2 sunny, Q3 rainy, and so on. Probability of starting state times probability of transforming from Q1 to Q2, Q2 to Q3. This is supposed to be a Q1, Q2. I've just written as a Q1, a Q2, but it is a Q1, Q2. So transforming from Q1 to Q2, Q2 to Q3, so on, Qn minus 1 to Qn. All the transmission probabilities you multiply, then you would get the probability of the sequence. This is joint probability, right? Probability of starting state times probability of transforming from Q1 to Q2, Q2 to Q3, so on, Qn minus 1 to Qn. The next one is the likelihood of the observation sequence given the state sequence. What is the probability of observation sequence x1 to xn given the state sequence q1 to qn? Okay, so this can be taken as product over all the emission probabilities q1 x1, q2 x2, so on, qn xn. Okay, suppose if I take this, what is the probability of x1 equal to true, x2 equal to false, x3 equal to true, given q1 sunny, q2 sunny, q3 rainy. So this can be written as, how can we write this? This can be written as probability of x1 given q1. I mean, I'm not writing the detail. x1 is true, q1 is sunny, times probability of x2 given q2 times probability of x3 given q3. Okay, so which is probability of x1, x2, x3 given q1, q2, q3. Right. So next thing is joint likelihood and likelihood of an observation sequence and a path. Both the things, observation sequence and state sequence. What is given to us? Given theta is given to us, which means that parameters pi a and b. Okay, so this can be computed. This we have already solved one problem. So this is equivalent to probability of q1 and probability of q2 given q1, q3 given q2, and probability of q1 given x1, probability of x1 given q1, x2 given q2, x3 given q3. All that probabilities you multiply, you will get this. And likelihood of state sequence with respect to hidden Markov model with parameters q, theta. That means here we do not have any information about the state sequence q. Okay, so in that case, what we do, we have to consider all the possible sequences for q. Okay, so all the possible sequences. Suppose 3 days are there. What are the all possible sequences? It can be sunny, 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 cloudy, or sunny, cloudy, sunny, sunny, rainy, sunny, or sunny, rainy, cloudy. All possibilities you have to consider and take the probability over that, sum over that probabilities. So this we have already computed. Second day was missing no, in one of the examples, and there we have considered all the possibilities and computed, right? Okay, so fundamental problems to summarize. HMM provides solution to 3 fundamental problems: evaluation problem, decoding problem, and learning parameters. What is evaluation problem? In this, we have given information about A, B, and pi and sequence of observations. We need to just find the probability of that sequence of observations. Okay, and the second case is decoding problem, in which we have given information about A, B, pi and the observation sequence also. We just need to find the optimal state sequence for this observation. So we need to find probability of q given x and theta. So this also we have seen. In the learning parameters, we have given observation sequence and the dimension n, which means how many number of states. So find the model AB pi that maximizes the probability of. So you have to learn parameters here, A, B, and pi. So these are the three fundamental problems. This application is there in the speech recognition because speech has got temporal structure, right? It depends on the sequence that you pronounce, right? So it has got some temporal structure and it can be encoded as a sequence of spectral vectors spanning the audio frequency range. So therefore, hidden Markov models provides a natural framework for this speech recognition model. Okay, so how do we do this? We decode or we convert the input audio form into sequence of fixed size acoustic vectors. Or in other words, we extract features from this audio waveform. So once we extract features, we have got the sequence of vectors x1 to xn. So these are our observations. In our umbrella example, these are equivalent to umbrellas, right? Whether the caretaker bringing an umbrella or not. So these are your observations, right? And the decoder attempts to find the sequence of words which is most likely to have generated X. Right. So what are we interested in? We have observed X and we are interested in predicting the sequence of words that would have generated this X. So if you see the umbrella case, what are we doing? We know the sequence of observations about the umbrella. We are trying to predict the sequence of days or the states that would have likely to have generated these umbrella observations. Right. So to map, this word sequence is equivalent to state sequence in our case, like whether it is sunny or rainy or cloudy, something like that. And this X in this case is a features, but in that case it is equivalent to the umbrellas. So the acoustic vectors is equivalent to our umbrella observations. Remember, here X is a vector, not just a single observation, single value, like in case of that. So to compare this with other example, the acoustic feature vectors are our observations corresponding to umbrella observations and the word sequence corresponding to weather on successive days. And maybe probably one day corresponding to about 10 milliseconds in this. And hidden state sequence of hidden Markov models for speech production. So and words can also be represented as a sequence of phonics, like hello can be represented as a H followed by E, then by L and O, the word in the word hello. So this can also be modeled using left-right hidden Markov model. Right. So this is a very good tutorial for this, from which I have prepared the slides in fact. So you can go through them if you're interested. Right. Thank you. Happy learning. We'll take a break. Before then, if you have any queries, I'll take. Any queries? Any queries?
Excuse me, sir. Sir,
Yeah.
can we model any text classification problem over hidden Markov models or any other generalized in speech recognition is also a good application, but in
Yeah,
general,
wherever the sequence or the temporal patterns are there, all those applications can be modeled using hidden Markov model. But only thing that you have to acquire the statistics that are required for that model.
yeah, that's okay, sir. I mean, model is also quite interesting. So one more thing is that can we have some analogy of this hidden Markov models like to the standard ML models where we have feature vectors and parameters, the weights, feature weights. So in that sense, can we have are our observations features a kind of thing or I mean,
Observations are the features. We have seen in the speech recognition, no, that our
yes.
observations are the features, and the sequence of labels that you need to predict are the your weather sequences.
Oh,
In
class
this
level
case, yeah,
was
yeah. Sequence of labels. Sequence is yeah, because
okay.
sequence is important.
Okay, okay, sir.
Yeah.
Thank you, sir.
Is that clear, Prashant?
Yes, sir.
Yeah. So any other query? All right, then we'll take 15 minutes break and come back by 6:40. Okay, thank you. Welcome back. Shall we start?
Yes, sir.
Yeah, thanks. So the topic of this session is decision trees. Decision trees. Is my screen visible? Am I audible?
Yes, sir.
Okay. Okay. Thanks. So we're going to cover decision trees, which is one of the model for the classification and also for the regression problems people use. But we're going to discuss it from the perspective of classification in this session. Right. So what is decision trees? Like we have seen one example, classifying insect, whether it is a cattleya or grasshopper. So we have discussed two features to describe an insect. One is abdominal length, another one is antennal length. Okay. So the decision tree asks for a sequence of decisions, and based on that, it will, based on the sequence of decisions, it learns a rule, and based on that rules, it classifies the objects. Like for example, if you see this particular case, given a new instance, where is it? Where the new instance is here. Okay, so somewhere here. Okay, so the first decision rule that it is asking is whether the abdominal length greater than 7.1 or not. Greater than 7.19 cases are this side. So there is no ambiguity for those kind of cases. If it is greater than 7.1, then it is surely candidate, isn't it? So you're classifying that as candidate. If it is not, then there is some ambiguity. You have to go for another question. What is the another question? Antenna length greater than 6.0. If it is so, then you will classify it as candidate. Otherwise, you will classify it as grasshopper. So if you see this particular example, whose abdominal length is around 4.5 and antenna length is 5. So abdominal length 4.5, which is less than 7.1. So you're taking a decision, following a path of no. So this one, right? So antenna length greater than 6.0. No, this antenna length is 5. So we follow this path and finally classify it as grasshopper. Okay, so if you observe this, at each and every node, we are asking some questions. We are taking some decisions. Okay, and this, according to this decision, we are following the path of the decision tree and we are taking another decision and so on, finally reaching to the leaf node where you are classifying the insects, sorry, objects. Right. So if you see another example, this is another example tree where this is an example of whether a person buys a computer or not. Okay, so we have got three attributes: age of a person, whether he is a student or not, credit rating. Okay, so age takes three attributes: youth, middle-aged, and senior. So for each of these attributes, we have different paths. So at the root node, we are asking a question about the age. If the age is youth, okay, then you're coming here asking whether he is a student or not. If he is a student, yes, then he buys a computer. If he's a middle-aged person, then you're directly taking a decision that you buys computer. If he's a senior, if credit rating is fair, then he'll not purchase computer. Senior, his credit rating is excellent, then he will purchase computer, right? So now the question is, how do you construct this decision tree? So given a decision tree, we know how to classify a new instance. This decision tree is one of the model, right? So given a decision tree, we understood how to classify a new instance, right? But how do we construct this decision tree? Is the question. How do we decide that A should be in the root node, a student should be in the left side node, or credit rating should be this node? How do we decide that? Is the question. Okay, so we'll see how to do that. Okay, so here the leaf nodes are the class predictions and intermediate nodes are the attribute value tests. We'll test attribute values in the intermediate nodes, and edges represents the attribute values. We test the attributes in the intermediate nodes, and edges represent the attribute values. Attribute values. Right. So if you see the decision tree schematic, we take the training data set in which we have got multiple attributes, let's say A1, A2, A3, so on, A5. And we select one of the attribute here at the dot node. Let's say it is A4. And based on this attribute A4 values, we divide the data further. Right. So X is all X, Y, Z are the three possible values for this A4. Okay. And these are all the instances that take value X. And these are all the instances that take value Y. And these are all the instances that take value Z. Okay. So if you select one attribute, that attribute can take number of possible values. Let's say if it is 3, X, Y, Z. And these are all the instances that take value X. These are all the instances that take value Y. And these are all the instances that take value Z. Okay. Suppose if this is the target value is to predict the color. Okay. So color of an object. Okay. So if you see this is the node which is pure red. It means all the instances with value Z on attribute A4 are taking target value as red. It means it is a pure node. Okay, so a pure node because all the instances are belong to the same class, red class. But if you see here, the classes are belong to multiple colors. So the instances are belong to multiple colors. So there is no purity at that nodes. If there is no purity at that nodes, you have to divide it further and take the decision based on the another level nodes. So these two are the impure nodes. Okay. So I'll ask you a very simple question, very general question, right? Suppose 2 cups are given to you. Both of them are milk cups. Okay. So in one cup, 100% milk. In another cup, 50% milk and 50% water. Which cup is pure? Which cup is pure?
First one.
Pure milk. Okay, the one with 100% milk is the pure milk, right? So pure cup, right? So here also, all the instances are belong to one class. That is why we are saying it as pure. But if you see, all the instances are not belong to one class. The mix of classes at that node. So we call it as a impure node. Right? So how to apply the test data once we construct the decision tree? Okay, we'll see that first and then we'll see how to construct a decision tree. So we start from the root node and we check for the attribute. So that the root node we have refund attribute and refund is taking value no at the test data. Right. So we follow the no path. So because the attribute value is no, we follow this path. Then the next attribute is taking about the marital status. So marital status, the value that the test instance is taking is married, right? So we follow this path, married. Then finally we are classifying as no, means whether he would cheat or not, we are assigning a label called no. Okay, we assign cheat to no. Right. So now the question is how to build a decision tree. We have seen what is decision tree and given a decision tree model, how to classify a new instance. But now the question is, how do we build a decision tree? How do we get a decision tree? So we follow greedy strategy to construct a decision tree. It means we split the records based on the attribute test that optimizes certain criterion. So we select some criterion and we select the attribute that maximizes that criterion. What is that criterion? We'll see that. Don't worry about it. So based on some criterion and the attribute that maximizes that criterion, we select the attribute. Okay, so there are a few issues here. What are the issues? Issues are determining how to split the records, how to specify the attribute test condition, how to determine the best split, and whether determine when to stop splitting. So all these are the issues we're going to address one by one. So we'll see first how to specify the attribute test condition. How to specify the attribute test condition. So the idea is choose the attribute that leads to the greatest increase in the purity. So we have seen what is purity, right? Right. So we'll select the attribute that leads to the greatest increase in the purity. Right. And it also depends on the attribute types. We specify the attribute test condition based on the attribute types also. Right. Right. For example, nominal, ordinal, continuous. There are different types of attributes, no? Nominal, ordinal, continuous. Continuous is the continuous value that we have already seen. Ordinal and nominal are the discrete values. The difference between them is nominal treats each and every class equally, whereas ordinal, there is some, equally means there is no relation between the individual classes. There is no hierarchy of between the individual classes. Whereas ordinal, if you take, there is some relation. Like for example, if you take rating, whether you would give 1 or 2 or 3 or 4 or 5, or whether you give average rating, good rating, or very good rating, or poor rating. Okay, so yeah, low, medium, high. Yeah, so there is some relation, right? Low is less than medium, medium is less than high. So there is some relation between the attributes. This we call as ordinal. There is some order exists in the attributes. Right, both of them are discrete, right? And it also depends on number of ways to split, whether you are going for two-way split or multi-way split. We'll see what is two-way split and what is multi-way split. So multi-way split means we may use as many partitions as many number of distinct values we have. For example, if you take car type as the attribute, car type may be taking three different values: family, sports, and luxury, right? So you partition into three different. You make three different partitions: family type one partition, sports one partition, luxury another partition. So as many number of distinct values as you have, make those many number of partitions. Binary split means we divide the data into only two subsets. So need to find the optimal partitioning here. So whether you have to split family, sports versus luxury, or sports, luxury versus family, or family, luxury versus sport. All the possible combinations you have to see. Binary means two should come one side and one should be other side, right? So what should be the optimal partition you need to determine. And this is, you need not check all the combinations if the data is ordinal. Like for example, small, medium and large. Okay, so you can check small, medium versus large and medium, large versus small. But you need not check small, large versus medium. It doesn't make any sense, right? Right? Small, large versus medium, right? So you need not check for that kind of split in case of ordinal data. Right. And the next question is splitting based on the, the next one is splitting based on the continuous attributes. So far we have seen the discrete attributes, right? Small, medium, large, all these are the discrete attributes. Suppose if the attributes are continuous, then how do we split? There are different ways of handling continuous data. One is discretization. It means convert this continuous data to a categorical data. Right, so to form an ordinal categorical attribute. This can be done in two ways. One way is static, the other way is dynamic. Static is discrete ones at the beginning by setting up some threshold. The other way is ranges can be found by equal interval bucketing, equal frequency bucketing or clustering. So this is a dynamic way of discretization. In both the ways, we try to map this continuous data to a categorical attributes. Right. The other one is binary decisions. Binary decisions like whether attribute greater than some threshold or less than some threshold. Okay. So consider all the possible split and find the best cut. Different values for the threshold you can try and see which is the best cut. Okay, and this is more computationally more intensive because you have to try for the all possible splits and see the best split. Right. So here the actual intuition starts. So please be attentive. Okay. So I have questions to you. Right. Suppose I have a drawer. Okay. In that drawer, I have balls, color balls. Okay. I have two drawers. In one drawer, I have got 5 red color balls and 5 blue color balls. And in the second drawer, I have got 9 red color balls and 1 blue color ball. Okay, so which is more pure? Which is more pure among these two? Or which is more impure among these two? Shall I repeat the question? I've got two drawers, and in both of the drawers, I've got the colored balls. In first drawer, I've got 5 red and 5 blue, and in the second drawer, I've got uh, 9 red color and 1 blue color ball. Okay, so which one is more impure or which one is more pure? Okay, so Prashant said first one is more impure. Okay, good. First drawer is impure. Good, good. So the first drawer is more impure, isn't it? Because equal number of balls from both red and blue colors, isn't it? So we say that the first one is more impure and the second one is close to the pure. We will not say it is pure, but it is close to the pure, right? So let's take this example. Right. So you whether these are the 3 attributes of the problem, whether a person won car or not. Sorry, won car or not, car type and student ID. Whether student won car or not, car type and student ID. Okay. And before splitting based on any record, the actual data has got 10 records of class 0 and 10 records of class 1. Okay, 10 records of class 0 and 10 records of class 1, and it has got 3 attributes: student ID, car type, and won car. Right, now the question is, which test condition is the best? Student ID, or car type, or won car? Let's see. If I split based on won car is taking 2 attributes, yes and no. Okay, won car is taking 2 attributes, yes or no. Okay, so if I split based on them, at this node, I am getting 6 instances of class 0 and 4 instances of class 1. And at this node, I am getting 4 instances of class 0 and 6 instances of class 1. Similarly, if I split based on card type, it has got 3 values for card type: family, sports, and luxury. And these are the class distribution at each and every node. Right. And similarly, if I split based on student ID, because student ID is unique, I've got 10 different values for this student IDs given to C20. Okay, and each one of them, the class distribution is like either it is C0 or class 0 or class 1. Okay, 20 different. Now tell me, which test condition is best among these 3? Quickly, anyone? Which test condition is best? Or which condition do you think it is worst? Let me put it this way. Which test condition you think it is worst among these 3?
First one.
Sorry?
First one, sir.
Oh, you're saying worst or best, sir?
Worst, sir. Worst.
Worst is first one you're saying. Okay, yeah. So somebody said worst is student ID. Okay. So, sir, can you please explain why do you think that is the worst condition?
Sir, it is more impure. This is why it can be like that.
But there is student ID which is more impure than one card, right? If you see here, the ratio is 60% class 0, 40% class 1. At this node, class 0 40% and class 1 60%. But if you see here, class 0 50%, class 1 50%. Both are
Sorry,
equal
sorry.
at all the nodes. Okay, so which one is more impure?
Last one, sir. Last.
The last one is more impure, therefore this is the worst. So ignore this. Okay, so now coming back to here. So among these two, which one is worst or which one is best? Among these two. Card type is best or worst?
Best.
Best. Card type is best because this is leading to a more purity. Isn't it? Isn't it? So if you see this, if you if you split based on card type, that is leading to impurity. But if you split based on card type, that is leading to more purity. So this is completely 100% pure, but this is close to pure because around 85% class 1 and 15% class 0. This is also 75% class 1, 25% class 0. Okay, so this is leading to more purity as compared to other two attributes. So which one you have to select? The
Type.
attribute that is leading to more purity,
Purity.
right? So you have to select that attribute, right? So how do we define that purity? Okay, we'll see that. So we follow greedy approach. Nodes with homogeneous class distribution are preferred. So we need a measure of node purity. So if you see this class 0, 5, class 1, 5, these have got non-homogeneous classes, high degree of impurity. If you see this class 0, 9 and class 1, 1, this has got homogeneous classes, low degree of impurity. Right. So how do we define this impurity or purity? We cannot always just check like this and determine whether it is pure or impure. We should have some measure to define the purity or impurity. So these are the measures of node impurity: entropy, Gini index, and misclassification error. Okay, so we're gonna see entropy in this session. Gini index is similar kind of measure to determine the node impurity or purity. Right. So what is entropy? Entropy or impurity of a set of examples is relative to a binary classification. It means it is defined in relative to binary classification, but it can be extended to multi-class classification very easily. Okay, so assume that you have two classes, class 0 and class 1. Okay, so you're saying probability of class 0 times log of probability of 0, class 0, and probability 1, P1 log P1, P1 log P1. So minus P1 log P1 minus P0 log P0. Okay, where P1 is the fraction of positive examples and P0 is the fraction of negative examples. Okay, so when this value would be 0, when all the examples are in one category, then the entropy will be 0. When all the examples are in one class, it means what? Suppose if all the examples belong to class 0, C0 10, C1 is 1, 0. It means all the instances belong to class 0, right? So in that case, what is the fraction of negative examples? P1 is 0, isn't it? And P0 is 1. P0 is 1, right? P1 is 0, P0 is 1. Correct. So if I substitute them in this, P1 times 0 times this is 0. P1 1 times log 1, which is 0. So the total thing is 0. Which means what? When all the instances belong to one class, it means when the node is very pure, this entropy is giving 0. So because it means impurity is 0. Because entropy is a measure of impurity, entropy is 0 when all the instances belong to one category. Okay, if the examples are equally mixed, then it is the highest level of impurity, isn't it? Equally mixed means 50%, 50% means then it is highest form of impurity. So we should get maximum value of impurity for this entropy, maximum value for this entropy. And the maximum value possible is 1. Okay, so let us see whether we're getting that or not. Okay, so P0 is 0.5 and P1 is 0.5. Okay, so substitute that and see, you will get 1, maximum of 1. And similarly, this you can define it for multi-class also like this. Sum over I equal to 1 to n minus pi log pi. Okay, so this is also same. Sum over I equal to 0, comma 1 minus pi log pi. Okay, so instead of 0, 1, we are generalizing it to I equal to 1 to c for multi-class classification problem. Right. So if you see the figure, this is the entropy and the fraction of positives. If fraction of positives is 0, it means one level of impurity. All the classes belongs to negative class. So in that case, we are getting entropy 0. And other extreme is all the classes belongs to positive class. Right. So this is also entropy 0. In both the cases, impurity is 0 because they're completely pure. All the instances belong to only one class. If you see the highest impurity, which is equally belong 0.5, I mean 50% to class 0 and 50% to class 1, then the highest peak you will get here. Okay, which is 1. If you have some fraction, like for example 80% or 90% belong to class 1 and 10% belongs to class 0, this case, you would get around 0.3 impurity. Okay, so based on the impurity level, the entropy will be measured, right? So entropy is proportional to impurity, right? So this is how you can get impurity. Now, I'm introducing another term, information gain. Please be little careful here, right? If you don't understand this, you'll not understand the intuition behind this, right? So the information gain of an attribute F is expected reduction in the entropy resulting from splitting on the feature. Okay, so I'll explain you in very simple words. This is like you measure the entropy of the data before you split based on one attribute. Okay, so let's say here the entropy is E of S. Now split it based on one attribute, let's say A1. Okay, now measure the impurity here, impurity here, impurity here. Take the impurities in the corresponding fractions. Okay, like average kind of. Right, average is not strict average. Suppose if you have got 10 instances here, 20 instances here, 30 instances here, you take 10 by 10 plus 20 plus 30 weightage for this. 20 by 10 plus 20 plus 30 weightage here, and so on, like that. Okay, so now what is it saying? What gain is saying is that if this split is reducing the impurity here, okay, then this is a good attribute. Okay, so whichever attribute is reducing the impurity at the root node, at the parent node, that attribute is the best attribute. Got the point? So before you select any attribute, compute the impurity. Now based on A1 you split and compute the entropy, A2 you split, based on that you compute the entropy, and so on. So whichever the attribute is reducing this impurity more, that attribute is the best attribute. Whichever attribute reducing the impurity more, that attribute is the best attribute. Okay, so this reduction in impurity is measured using the gain. Reduction in impurity is measured using gain. Okay, so gain of S comma F, where F is a particular feature, is equivalent to entropy of S. It means without F, without any feature, you measure the entropy. That is entropy of S, which is this impurity at the parent node. Now you measure entropy with respect to each and every possible value of that F. Okay, so this is one possible value. You measure entropy, which is SV. This is another. You measure entropy. It is another. You measure entropy. And multiply it with corresponding fraction. Okay, number of instances belong to that particular value divided by the total number of instances. Right? Yeah, weighted average, Prashant. Yes, good. Right. So whichever like this, you do this practice for all the features. Feature 1, feature 2, so on, feature D. Okay, so whichever attribute, whichever feature gets more gain, which is reducing this impurity more. Okay, you select that attribute at the root. Repeat this procedure for the intermediate nodes. So entropy of each resulting subset weighted by its relevant size. Okay, so weighted by its relevant size. So this one. Right. So any query here, please feel free to ask, and then we'll proceed to the example. Any query? Do you, agree with this intuition or not? Okay, good. Right. So let's proceed. So this is the example. I've got 4 attributes: outlook, temperature, humidity. So what it is? There's some question. Example will make it more clear. Yes. So if you have any query, you feel free to ask me after this example. So this is the example. I've got 4 attributes: outlook, temperature, humidity, and wind. This is whether a person will play tennis or not. Day 1 to day 14, based on the weather of the, based on the attributes of the day, like outlook, temperature, humidity, and wind are the parameters that defines the features that defines the day. Okay, and these are the decisions. He will know or yes, whether he will play tennis or not. Now, entropy of S. Okay, so this is the whole data set S. Okay, so what is entropy of S? How many positive instances? How many S? How many total instances? Day 1 to day 14. So therefore, 14 instances. Out of 14, how many of them are S? 9 are S. Good. Out of how many of them are no? 5. So what is P positive and what is P negative?
P positive is 9.
P positive is 9 by 14, madam, because fraction of positive instances.
Okay, 9 by 14.
9 by 14 and P
5
negative
by-
is 5 by
14.
14. So substitute them in the formula. You would get the entropy as minus 9 by 14 log 9 by 14 minus 5 by 14 log 5 by 14. So this is equivalent to 0.94, which is entropy of S, which means entropy in the or impurity in the data set. Impurity in the data set. Right. Now try to split based on the individual features. Let's take outlook, let's take temperature, humidity, wind, and see how much reduction in impurity is happening with respect to each of these features. Okay, so let's take outlook. So if I take outlook, what are the possible values for outlook? What are the possible values for outlook? How many are the 3 unique values? Sunny, overcast, and rain. Good. So let us compute entropy with respect to sunny. Outlook equivalent to sunny. Okay. So if you see outlook equivalent to sunny, how many instances are there with outlook equal to sunny? 1, 2, 3, 4, 5. 5 instances. How many of them are S and how many of them are no in the sunny? 1, 2, 3. 3 of them are no, 2 of them are S. Right? So P positive is 2 by 5 and P negative is 3 by 5. So substitute and get the entropy. Minus 2 by 5 log 2 by 5 minus 3 by 5 log 3 by 5. You would get 0.971. So this is the impurity with respect to this split. Okay, so take another split, another attribute value. What is that attribute value? Overcast. With respect to overcast, excuse me, 4 overcast are there. 1, 2, 3, 4. All of them are S, completely pure. If completely pure, what is the entropy value that you would get?
0.
0 we
0.
will get. So we've got 0 here. Then entropy or training. Right? 3 of the instances are plus, 2 of the instances are negative. So you will get same entropy as this because mix of the examples are same. So 0.971. Right? So we've got this. So we have completed one attribute. Let's go to the temperature. We have not estimated the gain of this attribute. We just computed the impurity with respect to each and every possible value of outlook. Let's do the same practice for temperature also. Temperature has got how many attribute values? Hot, mild, cool. 3 different possibilities. Right? Hot, mild, cool. So in entropy with respect to temperature hot is 1. Completely impure, 2 positive, 2 negative. Entropy with respect to temperature moderate, 4 positive, 2 negative, which is 0.998. Temperature with respect to cold, entropy with respect to temperature equal to cold, which is 0.811. Okay, so similarly, I do the same for humidity and wind also. Humidity, how many attribute values? 2 attribute values, right? Humidity.
2, sir.
Yeah, 2. And wind? Wind also 2. So I
Wind
compute
weak, strong. 2.
weak, strong. Yeah, 2. Right. Humidity high, I've computed entropy. Humidity normal, I've computed entropy. The next one is wind weak, wind strong. For both the things, I've computed entropy. Now I've got entropy for all the things. Only thing that I have to do is I have to compute the gain, which is the reduction in the impurity for each and every attribute. Okay, so let me compute gain for individual features. What is gain? Which is the reduction in the entropy. This is the impurity at the impurity of the data set, and this is the impurity after the feature selection, right? After reduction. Right. So I've computed gain for outlook, which is this feature. Okay. So which is equivalent to entropy of S, which is 0.94. We have computed that. Minus fraction of sunny examples times entropy of outlook equal to sunny, and fraction of overcast examples times entropy of outlook overcast, and fraction of rainy examples entropy of outlook equal to rainy. Okay, so these individual things we have already computed, right? How many sunny instances? 5 sunny instances. So 5 by 14 times corresponding entropy. How many overcast examples? 4 overcast times corresponding entropy. We have seen that overcast is pure, so entropy is 0. And similarly, you take the other one also. So the gain is 0.2465 here. So similarly, compute the gain for temperature, compute the gain for humidity and for wind using the same procedure. We compute the gain for the temperature. This is equivalent to 0.029. And gain for the humidity 0.151. Gain for wind is 0.048. Just to recall, gain of S comma outlook is 0.24, if I remember correctly. 2465. Oh, okay, 65. Okay, now you tell me which is the best attribute, outlook or temperature or humidity or wind?
Outlook.
Outlook is the best attribute because it is reducing the impurity more. Because it is reducing the impurity more, the gain is more. Okay, so we select the attribute with the maximum gain. Right? So we selected this attribute, the root attribute as the outlook. So the root condition is based on the outlook attribute. We check for the outlook. So this is fixed now. Right. So the outlook is fixed. Set the root node. We have got 14 instances, 9 of them are positive and 5 of them are negative, and Outlook is the attribute that we have selected. And Outlook takes 3 values, so therefore 3 paths: sunny, overcast, and rainy. So if you select sunny, these are the data instances that are coming here: day 1, day 2, day 8, day 9, day 11. Okay, and overcast, day 3, day 3, day 7, day 12, day 13. So these are the examples that are coming here. Rainy, remaining instances. Okay, so if you see 2 positive, 3 negative, 4 positive, 0 negative, 3 positive, 2 negative. So now how do you decide which attribute that you have to? Because it is completely pure, you are classifying it as S. All the instances belong to S. So classifying it as S because pure. Okay, now the question is, which attribute we have to select here? Which attribute we have to select here? Okay, similar procedure. You assume that this is a complete data set and repeat the procedure. Okay, clear? So you assume that that is a complete data set, repeat the procedure. Okay, very simple, right? So which attribute should we test here is again repeat the procedure. Outlook sunny, which means the entropy or impurity at this node. Okay, right? So which is 0.971. Outlook sunny and temperature hot. So you're checking for the other attributes. Among these 3, which is the attribute that you need to select for that node. Okay. So temperature taking 2 values, 3 values: temperature hot, temperature mild, temperature cool. For all 3 of them, measure the impurity. Okay. Similarly, do this for Outlook. Sorry, gain. Compute the gain for this, which is entropy of Outlook sunny minus the fraction of examples with Outlook sunny and temperature hot times entropy of Outlook sunny and temperature hot. Okay, so similarly do this, you will get gain as this. So repeat the procedure for gain equal to Outlook sunny and humidity high, Outlook sunny, humidity normal, and measure the corresponding gain. Okay, like this. And measure Outlook sunny and wind is weak, Outlook sunny, wind is strong. Okay, so measure the corresponding gain. Okay, you would get it. So now out of them, humidity has got more gain. So fix that attribute. Similarly, repeat the procedure for the rain also. Sorry, yeah. So humidity high. Humidity is taking 2 attribute, high and normal. And high, if you see, 0 positive and 3 negative. So what label that you would assign here? Huh? Negative we will assign, right? And here 2 positive, 0 negative. What label you would assign here? Positive. Right. So this is no, this is S. Right. So which attribute should we test here is again the same procedure. Okay. So only thing that you need to ensure that is that the attribute is not repeated in that path. So like for example, Outlook is already there in that path. You need not test again Outlook for Outlook. Okay. So check for the rest of the attribute: temperature, humidity, and wind. Okay. So it's not depth first. You can do this in any order. It's not necessarily in this order. We actually do this in the breadth first minute. Breadth first minute. But anything is fine. Any order you do, you will get the same thing. Okay. Because you are not restricting this to not to check humidity. You will check humidity here also, though it is selected here, because humidity is not coming any of the ancestors of this node. Okay.
Yes.
Yeah. Yeah. Right. So there are some problems. Sometimes you may get overfitting. So how to avoid overfitting in classification? Okay, so the generated tree may overfit to the training data sometimes. It means too many branches, Some may reflect anomalies due to noise and outliers. So it results in a poor accuracy for unseen examples, which is actually the overfitting problem, which performs well on the training data but not on the unseen examples on the test data. Okay, so two approaches to avoid this overfitting. One is preponing, another one is postponing. Preponing means you do not allow the tree to grow too big. Okay, so put some restrictor, right? Like you stop at level 3 or stop at level 4, level 5, based on the application at hand. Okay, so halt tree construction early. Do not split a node if this would result in a goodness measure falling below a certain threshold. Like for example, if gain is falling below a certain threshold, then also you stop. So put some condition such that tree will not grow too big. Okay, so post pruning, it is of course difficult to choose the appropriate threshold, what threshold that you should select such that you will stop this tree construction, which is difficult in the hyperparameter kind of. Another one is post pruning. Okay, so make the tree construction first according to the examples. Don't put any restriction. Make the tree construction first. Once the tree construction is done, validate that model or the tree. Okay. And if it is reducing the validation error, then try changing the tree. I'll explain you with example, don't worry. Like, for example, if this is the tree. Okay. So first of all, divide the data set into three parts. Training, validation or development data set, and testing. 3 data sets. Use the training data to build the tree. Okay. Now use this validation data for pruning. Okay. So how do you do this? So start with some node, from bottom to up fashion or something like that. So let's say that you have started here. Okay, you have started here. Cut off the branch at this node, all these branches. Okay, so before that, estimate the accuracy. Accuracy 1, say suppose, before pruning. Before cutting off the tree, accuracy is 1. Accuracy 1, you have stored in that. And now cut this node, these nodes at that point. Okay, and according to the validation that you measure the accuracy. Suppose you have got accuracy 2. Okay, so if accuracy 1 is greater than accuracy 2, what is that means? The tree before pruning is better or the tree after pruning is better?
Before.
Before pruning is better. Okay, so revert back this change. Okay, suppose if the accuracy 2 is greater than accuracy 1 less than accuracy 2, it means what? The tree after pruning is better. So you keep the tree like this, cut off this. Okay, so do this here, like that. So wherever, if the accuracy is improving, you can go to the higher level nodes, but if the accuracy is not improving, you can stop at that point. Okay, so this is one of the post-pruning technique. Like this, there are many post-pruning techniques. Okay, in which order you will, whether you will do it in the top-down fashion or bottom-up fashion, that is also one technique. Okay, so you start with the root node or you start with the leaf node. That is also another variant of this. Okay, so that's all. So these are the references. If you have any queries, you can ask. Otherwise, I'll quickly demonstrate and wind up the session. Very easy, no? We have completed it in, I think, less than 1 hour, 45 minutes. Any query? Any
Yes, sir,
doubt in the exam?
Yes, sir. Excuse me, sir. Yeah.
Yes.
Sorry. Actually, that decision boundary of this decision tree. I mean, how we can interpret? Is it linear or non-linear? It is a set of linear things. So, in which kind of classifier we can group this? Either linear classifier or
It's a
non-linear?
non-linear state. Definitely,
Yeah.
it is a non-linear.
Yeah, but a set of linear lines separating each decision.
Yeah.
Compartments type.
Mm.
Yeah.
Set up all those individual rules together, making it a strong nonlinear classifier.
Yes.
Individually, when you see them, they may be weak linear kind of classifiers, but when you combine them all of them together in a tree-like fashion, it will give you a strong nonlinear hypothesis.
So, but I feel that multi-class SVM where there is some discriminator order, that graph is similar to that of the decision boundary of this decision tree. Is there any link both of them, or is it coincidental?
No, I mean, the discriminating order is there in this also.
Yes, sir.
Yeah, both of them learns that.
Yes,
I'm
yes.
very happy that you have observed that. Means you are following the lectures. Thanks for that.
Thank you, sir. Yeah.
Any other? So, could you follow the lecture? Is it fine? Understood? Follow me. If you have any problem, please let me know. Have you understood or not?
Yes, sir.
Yeah. Thank you. So let's go to the implementation part. This is very simple. Uh, like um, like any other this one where any other machine learning algorithm and library, the same procedure. We import the library, we prepare the data set, we load the data set, prepare the data set, split the data set, build the model, predict the for the test. So the same procedure.
Sir, here will you show us how to prune the trees?
Pruning is you can give it in the as an option as a parameter in the decision tree model.
Okay, sir. Will you show those examples as well?
I think I have pre-pruning in that.
Okay, sir.
Yeah, I'll show you. Very simple technique, but you can choose the complex ones also. You can go through the parameters of the decision tree. What are they taking? And where am I? Okay. So this is importing the required libraries. So this is the model. Decision tree classifier from SQL lambda tree. Okay, so this is the model that I'm importing. Rest of the things I call metrics. This tree also I'm importing. I need not import the whole tree, but just I'm importing. I just want to plot the tree, how it looks like. Okay, so I can directly import that function like plot or something is there. Plot tree. I can import that directly. Plot tree. It is not. You need not require to import the whole thing. Plot tree. Okay. Right. So this is the data set. The student pass fail data set. Very simple data set that I've taken. You can take more complex data sets and see. So this is how the data set is looking like. I've just printed few records. First 5 records, head of it, self, daily, static, tuition, monthly are the attributes or the features. Pass or fail is the class. I'm just preparing the data set here, dropping out the last column, remaining things are X. Just the last column is Y. This is the data set. I'm just dividing the data into training and testing using train test split. 30% is the test set and remaining are the training data. So I've got X train, X test, Y train, Y test. So this is building decision tree model. The pattern is same. Classifier, I'm calling the classifier decision tree classifier. This is the model. Once I get the model, I have to fit the model to the training data. Okay, so I call the fit function and trying to build a model using this training data. So once the decision tree is ready, once the model is ready, you can predict it for the test. Predict test data. You will get the Y prediction. So we know Y test and Y prediction measure the accuracy. So I have used accuracy score here. Other metrics also you can use, like yesterday we have used a confusion matrix, classification report, any metric that you want. Accuracy is 100% in this case. So by default, so if you observe here, to the decision tree, I am not passing any argument here. I am not passing any argument to this decision tree classifier. So by default, it will take Gini index as the impurity to compute the impurity or the purity. Gini index. Okay. But if you want to change that criterion instead of Gini index, if you want to use entropy as the criterion, the one we have discussed in the slides, you can set the criterion. So the criterion is entropy. And madam, you have asked this, no? That different pruning techniques. Max
Yes.
depth equal to 3 I am setting. It means that I
Sir,
am restricting the
how
tree.
do you select this max depth, sir? That's what I'm wondering now.
This is again, madam, like hyperparameter. Max
Okay.
depth. Yeah, this is one of the things that you have to try.
Okay, sir.
And it also depends on the data pattern. Like for example, the max depth 3 is very wrong here. Why you tell me? Because I got 2 attributes only.
Yeah. Mm.
Anyhow, the depth will
Okay.
not exceed 2. Okay.
Exactly.
Yeah, so you base it on that number of users also, you can set that. I mean, you have, once you try for 3, 4 data set, you will get an idea how to set appropriately. I mean,
Understood.
what, at least you will get an idea that what range you can test.
Mhm.
You
Sir,
need not test the whole
I
range.
have, I have a doubt, sir. This hidden Markova model, sir,
Mm.
can you use it for classification purpose, hidden Markova models?
Yes, yes, yes,
Okay, but it needs a huge data, right, sir, for that?
yes, yes, yes.
Yeah.
Yeah, to get to actually at least to get those statistics, you require the huge data set.
Okay, fine. Thank you, sir.
All right. So again, I'm just changing this criterion and max depth I'm setting to 3. CLF dot fit I'm giving, then predict. Accuracy I'm just printing it. Right. Right. So if you want to visualize how the tree is looking like, you can plot. You can call plot underscore tree, which is also from this sklearn.tree. So which I have imported here. You can see sklearn.tree and importing plot. Okay, so this, you can see this, right? So entropy, with entropy also it is printing. Okay, so this means what? The condition is this. It's checking for a condition x1 less than or equal to 29 or not. It means attribute 1 is 20 less than or equal to 29 or not. Entropy is 0.985. Number of samples here are 7 and 4 are the positive samples, 3 are the negative samples or the other way. Okay, and if you see here at the second level, here the entropy is 0. It means all the samples are belong to only one class. Number of samples is 3. Value is 0, 3. It means 0 instances belong to one class, 3 instances belong to other class. Similarly here. Okay, so with that much detail, you can see the decision tree. You can visualize the decision tree. Right. So that's all. If you have any query, I'll take. Otherwise, we can wind up for the day.
Excuse me, sir.
Yes, yes.
Sir, on what basis we can select criteria? Because there are Gini index, gain ratio. So
Yeah, it
because
is
we are not
also
sure of,
attribute type also is one of the criteria. Usually, if the attribute type is, though it is not strict, I'm just telling you, this is one of the criteria that people follow. If the attribute is Zeni index, sorry, continuous, then people prefer Zeni index. Otherwise, this entropy kind of. But it is not necessary. But That is one of the criterion for the people who decide that.
Yeah, but there is a case if I take one criteria, I'm getting more accuracy. But you
So
cannot
in that
just
case, you can try with multiple criterion and see. See, all this, any of these things in
yes,
machine learning, okay,
yes,
you cannot judge one to be the best.
yes,
Okay, so one may be performing well in certain data set, and the other one may be performing well in the other data set. Okay,
yes,
even if you take the classifiers, we have these many number of classifiers. You cannot
yes,
judge them one of them as the best
yes,
because none of them works well for all the data sets.
yes,
Okay, so so you cannot judge it by
yes.
just looking at that.
Yes, mostly trial and error.
Yeah, yes. So far, this decision tree is state of the art when compared to the other techniques such as other neural networks. So these are all forms the basis for them, sir. Even the neural network is built on on the basis of logistic regression kind of models. Okay, so definitely this forms a basis for them. All the advanced models are based on the concepts of these underlying models. Okay, so concepts are same. Though they have performed very well in the current trend is deep learning and all that, they are performing very well on many problems. But the basis is this one. So if you have to, if you want to understand them, it is, I mean, you'll better understand when you understand these basic models. Right.
Sir, will you be taking some sessions on this data pre-processing, like handling this missing values, like those things?
No, sir, not planned.
Okay.
No, ma'am, not planned.
Because
We'll be
that's very
taking a
important, sir, to
session
get
on,
accuracy.
yeah, but we assume that that is easy and I mean everybody can self-explore that.
Okay,
So
sir.
we have covered more difficult topics. That is the
Understood.
reason.
Yeah.
Yeah. So, but dimensionality reduction and feature selection techniques are there. Tomorrow is that session, feature selection and dimensionality reduction.
Okay, sir. Thank you.
All right. So, if no queries, we'll wind up the session. Thank you very much.
Sir,
Yes.
sir, can you please suggest the name of any book which uses machine learning using Python?
Machine learning using Python, not readily there in my mind. I'll search it and let you know.
Okay, sir. Thank you.
Yeah. But pattern recognition and machine learning by Christopher Bishop is the good book for this machine learning.
Okay. Okay, sir.
Standard book. Yeah. All right. So thank you very much. Happy learning. Stay safe. Good night.
Thank you, sir.